So this is lesson 57 in Algebra 2, the ideal gas laws. And, you know, there's really not much to the ideal gas laws as far as what we're going to be doing here. It's just some real simple, well, if I can collie right. All right, let's get a thicker pen here. If we have the pressure of one item times its volume divided by its temperature, so the 1 here just represents its pressure times volume over temperature. The 1 just tells you that we're dealing with this particular element here. We could have put a Z down here. We could have drawn a picture of a mouse, whatever, just to show that all these are together. That equals the exact same thing, but we'll put a 2 down there to show we're dealing with a different substance there. All right. We have other gas laws where sometimes we're not given the temperature, sometimes we're not given the volume, sometimes we're not given the pressure. And those gas laws are called the Charles Law, Boyle's Law, and Gay-Lussac's Law. So I'm not really worried about the name. You get those in chemistry. But we have different formulas depending on that. So let's say, for instance, they did not give you the volume. So we cross both of those out and we have what's called Charles' law. Let's say that they don't give us the pressure. And that becomes Boyle's law. And let's say that they don't give us the temperature. That's Gay-Lussac's law right there. PV equals PV. All right? So we can come up with various things based on that. Bottom of page 245, it tells you what pressure is, because sometimes they won't tell you the pressure is such and such. They will just say there is 40 newtons per square meter, or 3 atmospheres, or 42 millimeters of mercury, or torrs, or pounds per cubic inch. Those are all measurements for pressure. And that first little bullet down there on the bottom of page 245 tells you what the different units are for pressure. For volume, you have liters, milliliters, and cubic centimeters. And for temperature, what we're going to do for temperature in this, because both of these temperatures are what is called Kelvin. Okay? So when we write Kelvin, Kelvin has the same scale that Celsius does, but it starts at gosh, this is a long time ago since I've done this. It starts at absolute 0. So 0 degrees Kelvin is absolute 0, which is negative 273 degrees Celsius. So absolute 0 is unattainable, but if it were, that would be absolutely no heat at all. There's no temperature at all. We've never been able to get anything that cold. So anyway, let's just go ahead and do some of these problems here. All right, so example 57.1. It says 4 liters of an ideal gas of 800 kelvins and a pressure, they give us a pressure of 100 newtons per square meter. All right. If the volume were increased to 10 liters and the temperature reduced to 600 kelvins, what would the pressure be? All right, so what they do is they give you an initial bit of information. And then they're saying we're going to increase, or we're going to make some changes in that, and we're going to put those numbers over here. So let's do that. 4 liters, that would be volume. So we're going to put a 4 right there for volume. Temperature is 800. And the pressure is 100. So those are my 3 numbers they gave me. And then they say the volume is increased to 10 liters. The temperature is reduced to 600. What is the pressure? All right, so notice we have 6 different things here. And in order for us to solve this, they have to give us 5 of them. And then the 6th one is what we're going to end up looking for, which in this one is the P, or the P, I guess it's the P2. Except that doesn't look like a 2. All right, so then we just cross multiply this information and then the other. Okay, and we just solve for P that way. And once we get P, we get 30 newtons per square meter. Now notice we get our units newtons per square meter because in the initial one right here they said it has a pressure of 100 newtons per square meter. So we just leave the endings the same. So if we're looking for pressure, we look at what pressure they gave us, and that's going to end up being the ending there. Alright, so let's continue down on the second example and see if I can erase and talk at the same time. I wish my eraser was bigger. Alright, so we have an initial pressure of a quantity of an ideal gas is 400 newtons per square meter. So that's my pressure. The initial temperature is 1200. The volume was held constant. Alright, when the volume is held constant, you don't need a volume. Okay, so that's a key thing there. So if it says the pressure was held constant or the temperature was held constant, that means you don't put that on there at all. You just leave it off. So here I've got the pressure, here I've got the temperature. I don't have a volume. It's not necessary because if the volume was, let's say if it was held constant, let's say it was 30 here, and then we have a 30 here because it didn't change. Well, both of these are multiplied by 30, so it just is going to reduce to what we're going to get without putting the 30 on there. So if the volume is constant, you don't even have to put it on there, or if the pressure, or if the temperature. Alright, what was the pressure? So this is what we're going to be looking for if the temperature was decreased to 900 kelvins. So multiply that and you get 3600, or I'm sorry, 36. 1, 2, 3, 4. There. 360,000 equals 1200 P. And you can cancel out 2 zeros here, 2 zeros here, and P. And we have 3,600 divided by 12 equals P, or P equals 300. And we're done. Alright, let's do one more, and then we will be done. This is kind of a breath of fresh air, isn't it? Not having to do anything that really tries your brain capacity. Let's leave that up there. The temperature of a quantity of an ideal gas was held constant. So I'm not going to have a temperature since it says it's held constant. So I'm just going to use that. The original pressure was 7 atmospheres. You don't have to understand what an atmosphere is. The original volume was 42. If the volume was reduced to 10, what is the final pressure? So we take this and divide by 10, cancel that out, and we multiply 7 times 42, divide that by 10, and we end up with 29.4 atmospheres, ATM. I don't remember. Seems like maybe they write it as, no, I think it's ATM. Alright, so that's it for lesson 57. No sense in me really going over any of the practice problems because, golly, you know, they're not too difficult there. I think you'll kind of have fun with those. Alright, so that's it for lesson 57.